Absolutely. So thanks so much for organizing this event. I think we should have this every year. This is something I'm a huge fan of. And of course, I'm a fan of data as well. But I'm going to talk a little bit about some of the cautionary notes of bad science, or if that's what you want to call BS, but I usually call it bullshit. Most over the last couple of years, I've been thinking a lot about the ways in which misinformation travels both in science, outside of science, and in society. But what amazes me is how science can be so resistant to BS. That's what's crazy. And I think at its foundation, science has this largely agreed upon set of data and procedures that we use to adjudicate disagreements. But really, a lot of it comes down to science just being relentlessly empirical. It's relentlessly empirical, and partly that's due to his success. And if you want to read a good book on this that just recently came out, Michael Strevin's book on this is fantastic. So what if we got to this world where I could make a statement in a slide presentation that looked like this? Science policy is relentlessly empirical. There's some goods and bads to that, but if it does get to that state, I think we have some cautionary notes to be aware of. So let's look at some of the other government agencies that use data and communicate with data, but also make some mistakes. So the Georgia State Department of Health during the COVID crisis, in the early parts of the COVID crisis last year, put out a heat map showing the different case counts in counties across Georgia. And it was at this time there was major debates going on about what to do: mask, no mask, close, don't close. This was on July 2nd. Then they posted another heat map on July 17th and said, well, look at the heat map. You make a decision for yourself. And if you look at the two and you look at the counties in red and the blue shades, it all kind of looks the same. Problem is, if you look at the bins, they're quite different. And when I talk to my students about these kinds of things, if you allow me to change the bins of a heat map or the bins of a histogram, I can tell any story I want. So it's not just enough to be relentlessly empirical. We have to create habits of mind, and we have to train our policymakers that are using this data to be careful with that data. And when I talk about calling BS and spotting BS, I always want to make sure people remember Hanlon's razor, which is never ascribed to malice, what can be adequately explained by incompetence. And better than that, never ascribe to incompetence what could be an understandable mistake. And in that case, to the defense of Georgia State Department of Health, they said, well, that was the automatic scaling of the software we're using. Well, that's even more reason to train both the consumers of this information and, very importantly, the producers of the information. And it's not isolated to state governments. During the pandemic, we saw cumulative plots, which, as far as I know, always go up when looking at the number of tests taken. And that's, I guess, one way to present it, but it's very similar to how Tim Cook was representing the explosive growth of iPhone sales when he took over in the early last decade. But really, a better graphic would have been quarterly sales, which would have told a much different story. The point here is that numbers appear to carry this authority. They're precise, they seem like science, they're objective, they almost come straight from nature, which is why 37% of all virtual talks include made-up statistics. So watch out for those. The thing is, it's not just about the way we use data specifically, but the techniques that we use data to make conclusions. So here's the thing that's disturbing to me. Everyone thinks they know that correlation doesn't imply causation. But are they sure about that? If you look at several studies that have come out of the 50 most shared health outcomes, half of the news articles that reported on those conflated causation. And even worse than that, a third of the actual journal articles misattribute causality. So it shows that, if even the researchers, the journalists aren't getting this right all the time, how can we expect the public to get it right? So we need to be careful of that. And even when you have careful studies, like this study that was a paper that reported an association between the lack of exercise and cancer risk. It doesn't mean that there's not a benefit of exercising, because it probably does reduce cancer risk, but that's not what this study showed. And that's not what Time reported. They talked about how it lowered risk. Of course, the US News Report was here talking about how exercise cuts cancer risk, or Los Angeles Times drives down. These are causative signatures, and that's something that we need to clean up starting at the policy level. Because what happens usually is that correlations, they're not prescriptive, but that's what they end up being. So the scientific paper might say moderate consumption of wine consumption is correlated with reduced risk of heart disease. The news report comes out saying red wine consumption reduces heart disease. The prescriptive claim says drink a glass of red wine with dinner to stave off heart disease. Now, again, it may be good to drink red wine. I love red wine, but this is not what we want when we're coming out of policies to get to this prescriptive claim. So here's the cautionary notes. train policymakers to spot and call BS, bad science, on data and machines. So let me give you one example and move to the next one. This was from my colleagues recently, a couple of weeks ago, where they showed how the machines that were deciding whether a radiograph, a patient had COVID or not, wasn't looking at anything within the actual radiograph. It was looking at silly markers on the side, whether it was lateral, which hospital, or things that had nothing to do with it. But everyone was so excited because the machines were going to predict who has COVID or not. The point is we need to be calling BS on the machines and the data. And so we train a lot of the students. And when I talk to the public, I say, don't worry about the black box most of the time. Focus on the data input or the output interpretation. One of the largest, most used trained data set in computer vision, which is going to drive our driverless cars, et cetera, make diagnoses in the hospital, is ImageNet and various other related images. And what we found just recently, even though it's been around for over 15 years, is that there's errors everywhere in this thing. A group at MIT found all sorts of errors, even the alternate errors. So you see here, it says it thinks it's a polar bear. The alternate was an elephant. That's no elephant that I know of. But it's understandable to have these mistakes, but it brings us back to an important point that was made yesterday by Zhao Li, that about his big data paradox, which is the more the data, the surer we can fool ourselves. So we have to be very careful about auditing and rewarding the auditing of the software and the data. So let me just mention one thing, even when we get to the point when we use data all the time, and that's data dependencies. We're going to be dependent on data in science policy, and I hope we are in some ways, but we have to be careful of the kinds of data dependencies. So in 2015, I remember when this announcement came out because I use bibliometric data and have for many, many years in my research. Microsoft Academic came out and said, we've got this new tool. We're going to make it available to the community and you can use it. And we were so excited. I remember talking at lunch. I said, this is great. Finally, it's going to be open to the community, not just to those that have access to these other really well-curated bibliometric data sets. And I remember at the time saying, this almost sounds too good to be true, because it reminded me of all the projects that Google had killed. There's a Google graveyard website, shows all the projects that they killed. And I hope they never killed Google Scholar, although I have my problems with Google Scholar. It wasn't going to be Microsoft, because there's a Microsoft site too. They have a graveyard site, but lo and behold, May 4th, last month, they killed the project. Now, they even cite, they look at the way that it's titled as expanding into new horizons. Now, and I can't blame Microsoft. They've provided a great resource, but we're becoming dependent on these kinds of data sets, and we need to think about that dependency because it affects the field. There were hundreds, probably thousands of papers using MAG, and now it's not going to be available in the same way. So let me end with my last cautionary note is to design metrics, because metrics follow directly from data that encourage good science, if we can define good science. And this is, as many people know, Goodhart's law, which is any observed statistical regulator will tend to collapse once pressure is placed upon it. But a better TLDR version is when a measure becomes a target, it ceases to be a good measure. And I'll give you one example and end here. So US News and World Report is something that all universities get so excited when it comes out. It's like a holiday, gifts are coming out. And one big part of those rankings is the class size. It's actually one of the highest of those, if in this black box that we know of and it's reported on. Here's an example of some of that data. I don't want to blame Marquette because they're one of the few universities that report this data in detail. So you see here, classes, there's 100 on one classes with classes of 5 or less. There's 122 of 150. So you say, oh, mean class size is 26. And that's how it would get reported in US News Report. But that's not how big the class is. If you ask a random professor, it's 26. Not so much if you ask a random student, because the majority of the students are in the larger classes. So that's something we call, my colleague and I call observation selection effects, which is a whole nother issue. So the real issue here is the average class size is 26, but the average experience class size is 51. So all these universities are playing the game to this metric, when in fact, they're making it worse for the student, the experience that the students are having. The point is, we need to be careful of the metrics we're using. And one last one of the most important laws in bullshit studies, if you allow me to call it that, is from Neil Postman. It talked about this in the 1960s, that at any given time, it's his third law, by the way, he's got other good laws, the chief source of bullshit with which we have to contend is ourselves. So our field, the science policy field, as we move forward using more data, we just need to be internally self-reflecting and be careful of that. So with that, I'll stop. Thank you. And thank you again to the organizers for putting on a great conference. I've really enjoyed the conversation so far.